Hi, it's Miss Carpenter here at Humble Pie Math. So today in our box, we have lots of things. We have a pencil, which represents it's time to practice. Put this theory into practice. We've got a little plant. We have 1, 2, 3 pottery vases. And we have our food truck. Okay, so what do these have to do with linear relations? Well, in all of these cases, we can use this to make a linear situation make sense. We can predict things, we can find patterns. So let's have a look at this one. For example, we have our food truck. With our food truck, if we have our linear equation and we want to use it, we first of all can take some information. So let's say we have it's going to cost us $200 to park our food truck. And then to run our food truck, it's going to cost us, say, $3 an hour. So it costs us $200 just to park it, and then it costs us $3 an hour to have the food truck going. Okay, so let's take and make a graph or a table of values. Let's start with our table of values. So we know right away that we're talking about time. Time, and time is marching on independently of whether or not the food truck is there. So that's our independent variable. And y is how much it's going to cost us. That's the money. Okay, whoops. So let's make a graph of x and y. So our x is going to be our time, and our y is going to be the cost. You can even go like this. Okay, here's our origin. And at 0, when we first arrive there, it's going to cost us $200 just to be there. 200. Now we're going to go up by 3. Well, hang on. If all this way, that'd be 100, that'd be 50, that'd be 10. We're going to have tiny increments. So we're going to do a little trick with our graph. We're going to say that this part from 0 to this spot right here where it's, say, well, we can pick where it's going to be, but let's pick 200 for simplicity's sake. So this is going to be $200. This is the cost in dollars. And this we can entitle cost for food truck. Because your graph should have a title. Okay, so the cost for the food truck is going to be 200. And then after that, we can say this is 205. This is 210. And see how now it's a graph that we can really read. Okay, and time starts out at 0. Then after an hour, 2 hours, 3 hours, and we're going to stay for 4 hours. So we can plot how much this is going to cost us. Okay, so our first one at time 0. Now what does this remind you of? If x is 0, we're looking at the y-intercept. So what is y when x is 0? Well, how much is it going to cost? It costs us $200 just to park there. So that is our y-intercept. We're going to start right there. Okay, from there, after 1 hour, we're going to be at 203. So we've gone up by $3. That makes sense because we have to add $3 every single time an hour passes. So 1 hour has gone by. Now we're at 203. So 1, 2, 3, 4, 5. 203 is right there. Line that up with our 1. There's our next value. After 2 hours, it's 206. 3 hours, it's going to be 209. And after our final hour, 4 hours, we're going to be 211. No. 212. That's right. Okay, so 206 will be right about there. And then this one will be right here. And this guy will be about here. Because we'll be at 212 at this point. Yeah. Okay, so we have a nice linear relation. And what we're going to say is that you have to stay full hours. It's like going to the hospital and paying for parking. You have to pay for the whole hour no matter what. So our first order of business is to say, okay, well, what's our y equals mx plus b? Well, y and x are going to be any of these values. Our y-intercept is when this is 0 and when it crosses the y-axis, so that's our b. And then our slope is going to be the difference between 2 points. So you can try any 2 points. I'm going to use point 206 is right here with 2. So that's my y value. And my change in y is from 206 to 203. And my change in x is 2 minus 1. So what is my slope? It's going to be 3 over 1. That means every single time I go up, 1, 2, 3, I go over 1. Up 1, 2, 3, I go over 1. That tells me my rate of change. So for a question like this, you can easily figure out your y equals mx plus b just by creating your equation like this. That would be the equation of this line. Why can't we put y and x in there? Because y and x are going to change. They aren't constant. What stays constant is that we have to have $3 every single hour. How many hours we stay changes. This doesn't change either. It's a constant as well. $200 we have to pay no matter what. When we start at time 0, we still have to pay $200. So that is constant, and we can write it in our equation. We cannot write the x and y because those are values that vary. Awesome. Okay, we're going to come up with 2 more examples. If I tell you that a potter, and this is from a real experience in Cuba, when a potter was making pottery and he could make it, one of these little vases, in under 5 minutes. So we're going to say 5 minutes. So how many vases he could make was dependent on the time. The time didn't change because he made more vases. So if we start out and he made 0 vases, that's at time 0. After 5 minutes, he could make 1 vase. After 10 minutes, he had made 2, and after 15 minutes, he had made all 3 vases. So if we do that on our graph, again, we're going to entitle it vases or time to create vases. Time is down here as it often is, almost always. That's our x, our y is here. And what is dependent on the time? How many of these we can make? 1, 2, or 3. It depends on how much time we have. So if we have 1 hour, 2 hours, that's going to be a lot of vases if we have 3 hours. If we have 5 minutes, 10 minutes, and 15 minutes. And then how many vases we can make. And just so it's clear, always label your axis and your graph. So I've got time here, vases here, time to create vases is here. Okay, I'm also going to write minutes so that we know. Now, is he creating, this is one of those graphs where you could make it continuous if you said that he is steadily making these vases, and really he is. He starts at 0. After 5 minutes, he's made 1, but the whole time he's been making it. Then after 10 minutes, he has finished or completed 2. But in this whole time, like he's got half a vase made right about here. So then up here, he has 3 vases made at the 15-minute mark. That's how we plot it. That's how we put our table of values. How do we have an equation? Well, we know we can't change the y because it changes. We can't put it in, What is the slope? We can put that in. And what is the y-intercept? Well, in this case, the y-intercept is 0 because it crosses the y-axis where it begins at the origin. It truly is the b for beginning. So that's 0. So once we write the equation, we can just erase the 0, but we'll leave it there for now. And what is our slope? So in this case, sometimes students will do this. If you have a grid or a graph paper and it goes like this, and you know, oh, this is 2 squares and this is 2 squares, I'm going to say my slope is 1 over 1. But in this case, this square is representing 5. So be careful with that. Look at this and say, what's my change? My change in x is 5. My change in y is 1. They're both positive, makes sense, because we're pushing the potato positive or pulling the sled. It's positive. The other thing that we have to notice is that we put our y value on top and our x value on the bottom. So our change in y over our change in x gives us the slope. So what was our change in y? It was 1. What was our change in x? It was 5. So our slope is 1/5. Can you have a fraction? Absolutely. It's easier to understand that I go up 1 and over 1, 2, 3, 4, 5 if you have a fraction. Some students will ask, can I make it a decimal? Well, if you have a decimal, that's going to be a really confusing thing to have to put on here because you're going to have to go, well, that is 0.2, so I'm going to go up 0.2 for every 1. Ew. Instead, whole number fractions, way easier. All fractions are whole numbers. Well, mostly. Okay, and our last example will be our plant. So our plant is growing the entire time. And we can say we're starting at time 0. Again, we've got time. Over here, we've got height. And we'll say in centimeters, and our time will be in months. Because I wanted to show you how you could have January, February, March, and then you could say, you could still do this as 1 after 1 month. Okay, and we'll say centimeters, 10 centimeters, 20, 30, 40. Our table of values for x and y, maybe you go and you measure your plant. So you measure it at the beginning of time. This is time, and this is height. When you measure the plant's height to start with, you're at time 0. Your height, we're going to say in this case, was 12 centimeters. So your plant height, right here, 12 centimeters at 0. That's going to be our b for beginning, where we begin on the y-axis. B is going to equal 12. We already know that. Then we have to figure out what our x and y values are going to be. So let's say in the question I told you that every single month we noticed that our plant grew 3 centimeters. So after 1 month, it was at 15 centimeters. After 2 months, 15 plus 3, 18. After 3 months, 18 plus 3, 21 centimeters. Okay. Starting at 10, not 0, starting at 12, I mean, then our plant is going to continue to grow. So after 1 month, we're at 15, which is right in the middle here. After 2 months, we're at 18, which is just 15, 16, 17, 18, 19, right about there. And then after 3 months, it's going to be 21. Now I did it this way because I wanted to show you, in this case, could I have drawn my graph differently? Absolutely. I could have gone 10, 20, and made this whole thing to stretch out my graph. Because this way it's showing very little rate of change, but it is a very little rate of change. It's only 3 centimeters every month. That's some slow growing. Now, is the plant only growing whenever we look at it? No. So this has to be all connected. These dots you have to connect. It is continuous. It is going to show us that the plant is growing all along, even if you're not watching. Okay, so then we can figure out our slope. So slope is going to be the change in y over the change in x. So the change in y is plus 3. The change in x is plus 1. That gives us a slope of 3. Now, I can encourage my students to write 3 over 1. That's so that when they're plotting points, they don't forget 1, 2, 3, I have to go over 1. I've gotten students who put their line straight up and down on the y-axis because they forget, okay, wait, or they're stumped. How come this isn't working? Oh yeah, I have to go over 1. Your slope technically is 3, but you can think of it as 3 over 1 if that helps you. Okay, and then all the y values can be whatever they are on our table of values, and our x values will be whichever one matches with whichever y value you're talking about at the time. So if you're talking about the y value 15, then this x is going to be 1. So that's our equation of the line. Okay, see you next time.